the what, the why, and the how of this very important conversion and conservation process as businesses opt to generate their own electrical power. We chose this particular topic today because of inquiries from our ever-growing audience who acknowledged it was a niche market, but because of its significance relative to the amount of energy produced and captured, it would be good to know more about it without getting overly involved in the complex engineering connected with it. In other words, keep it relatively basic and simple. For this reason, then, we're going to explore the area of large-scale energy recovery, starting with those industries who are already engaged or at least contemplating engagement of their own power generation. We'll look at some of the drivers which make them choose to invest the large CapEx dollars involved. We'll also explore the sources of the heat energy to be captured, with considerable emphasis for time reasons on the gas turbine, which is also the most prevalent heat source used in this combined heat and power. Examples, we'll also get into some examples of the heat transfer equipment used to capture this energy, also known as the HRSG, the heat recovery steam generator. And we'll discuss where this reclaimed energy may be applied. We'll acquaint you with some of the basic auxiliary devices employed in these system packages, which will augment or enhance the HRSG, including its basic control scheme. We'll get into that in the end. And then finally, we'll discuss an important factor one needs to consider before moving forward, and including the importance of selecting the best partner for the project. This becomes extremely important because in this business, this is really where the rubber meets the road, because each application is different and needs to be uniquely engineered to realize and optimize the ultimate objectives, whether it be energy conservation, whether it be emission reduction, peak loading, standby, meeting additional steam requirements, or all the above. Having the right partner that can deliver the entire or as much of the entire solution is very, very critical. So with that as a bit of overview, let's start with some definitions so we're all on the same page when these concepts or terms are mentioned during the presentation. You can see on the very top here we've got a kilowatt. That's 1,000 watts. A megawatt is 1,000,000 watts, or it's equivalent to 102 boiler horsepower. HRSG, as I mentioned, heat recovery steam generator. Combined heat and power, this can often cause confusion. Combined heat and power for either direct or indirect energy recovery and application of the thermal energy to the process. This might also be termed cogeneration. What would I mean by that? Well, if it's direct, in other words, I've got a turbine. It's exhausting lots of gas at a high temperature. I can take that right directly to some energy converters. Let's say it's a dryer, and I can use it directly off the turbine, or I can go through a boiler, secondary source, if you will, generate steam or hot water. So that's what I mean by that. But both of them, it's cogeneration or combined heat and power. I can also have combined heat and power when I have a turbine which is driving a generator to generate electricity, but also the off gases then are going to a heat recovery steam generator, which it is then being used to drive a secondary turbine, a steam turbine now in this case, to generate additional electrical power. That we would refer to as combined cycle. But they're both combined heat and power, okay? Now, if we take a look at what's going on in this business as far as large-scale energy recovery, let's just familiarize ourselves with the basic concepts that are out there. This is the traditional plant. We've got a boiler here that's generating steam or hot water, and that's obviously being used for cooling or heating. Of course, in this particular case, if we're talking about cooling, it would be going to an absorber. Most of the time, it's a centrifugal chiller that's used for cooling in most of these buildings, but just for example's sake. So I'm taking the steam, and I'm taking care of all my process and building needs directly from the boiler. Then I'm buying my electrical needs right from a utility through the grid. So that's the traditional plant. I can get involved in combined heat and power where I've got a boiler that is now my motive force. Okay, I'm generating steam, driving a steam turbine, which then in turn is driving a generator and producing my electrical needs within the plant. So I'm controlling all of it now. Now I'm in the electrical generation business. I can also take part of that steam and get involved in cooling or heating or process. Again, combined heat and power, where the motive force all begins with a fuel-fired boiler. Now, the other thing that I can do with combined heat and power is I can take a gas turbine, such as you see here, which is now driving a generator, which is then providing all of my utility needs, electrical utility needs within my building, and I'm taking the off gases now, which are relatively hot, and we'll get into that, relatively hot, going into a heat recovery, HRSG, producing steam or hot water for my process or building heating needs, comfort heating or cooling. Now, the other thing I could do is, rather than having a gas turbine, I could have a reciprocal engine doing the same thing. It's got the off gas going to my heat recovery boiler, HRSG, and driving a generator, producing the electrical power for my building. So rather than the gas turbine, I'm using a reciprocal engine. This is then called combined heat and power, or a combined cycle, if this boiler here, or HRSG, was driving a steam turbine. Now, another excellent source of heat energy, thermal energy, would be a thermal oxidizer, as you see here. This then, and a thermal oxidizer, by the way, for those of you that don't know what it is, it's really a fume incinerator. And it's destroying hazardous air pollutants and VOCs. The neat thing about these thermal oxidizers is they've got many pounds of gas coming out of them at a very, very high temperature. We're talking maybe 1,500 degrees that we can use. Whereas with the gas turbine that I talked about previously, you're talking maybe 900 degrees coming out of it. Now, going back to our gas turbine. The gas turbine has got basically 3 cycles that can be used within it. And by the way, as you can see on the screen too, the normal range in terms of capacity for these gas turbines is between 500 kilowatts and 250 megawatts. So they generate a lot of power, okay? A wide range with these gas turbines. As far as the cycles are concerned, the simple cycle that you see here, what I'm doing with my gas turbine is I'm driving a generator, and that's all I'm doing. The gas that's coming out of it at 900 degrees, the pounds of gas, is being wasted. That would be a simple cycle. I could then get into the next one here, which is simple cycle with heat recovery. Again, that's kind of what I mentioned before. Now I'm taking these pounds of gas coming off this gas turbine, relatively hot, about 900 degrees, and I'm taking it into some kind of an exchanger and taking those BTUs and applying it to some useful purpose. The other thing I could do lastly here is a simple cycle with HRSG, which is what we're really talking about today. Now I'm taking that thermal energy, putting it into a boiler, if you will, generating steam or hot water, and applying it to my building. So that's what these gas turbines will do. Now, as far as how they work, they take ambient air, they then compress it, heat it, and then allow it to expand. And when that gas expands, that's really a fluid. Gas is really a fluid. It turns those turbine blades. Okay? Now, very, very important that we don't condense in here, because those turbine blades will get attacked by that condensate. So you want to make sure, and that's the way this turbine is designed, so it will not condense within it. Okay? Because that would cause some real problems within the turbine itself. Now, as far as the various types of industries that are using these gas turbines today, as I mentioned, you can see them on the screen. And I might say also that the reason that these companies are looking at this type of recovery, the combined heat and power, is for a number of reasons. We'll get into that in a second. But one of the main things is that when we buy power off the grid, These utilities try to do the best they possibly can, but at best we're losing 50% of that power by the time it gets to the user. Now, these users are large utility customers. So the amount of energy or amount of electrical power that they're buying is extensive. And of course, with a 50% loss, these utilities have to pick up that difference. So these demand rates and these charges that these companies are being charged is quite large. So if we take a look at what the drivers are as far as why are people even looking at combined heat and power, the main driver, of course, is cost reduction. Okay? The next thing is the electrical reliability. We all know what happened at the Super Bowl not long ago, right? When they had a huge power outage. And there was auxiliary power that was able to bring those lights back up to maybe only light half that facility. So something happened with that grid. I'm not even sure if it was ever really totally resolved. But that's what these companies are looking at. They've got critical loads. They've got processes that they can't afford to have a lapse. So reliability is another major driver. And they also they want to be able to supplement existing steam capacity. Maybe, as I show in this example here, maybe they do. They want to get away from the centrifugal chiller and put in an absorber for one reason or another. All right? Or there might be some other process that goes in and they need additional steam or hot water. So they might be looking at this turbine, or they might be looking at this thermal oxidizer as another source of energy to be able to meet that particular need. And then the other thing is the backup reliability. Their fuel-fired boiler, if that goes down, they're dead in the water. So now maybe they could take that turbine or they could take that thermal oxidizer and they could use it through a HRSG to be able to give them the backup they need should there be a problem with that fuel-fired boiler. So those are the main reasons. Now, let me kind of put things in perspective here. When we're talking about a 5 megawatt load, we've got a gas turbine that's generating about 150,000 pounds of gas per hour at 900 degrees, as I mentioned. Now, that pound of gas can be converted to about 25,000 pounds per hour of steam. Now, that's equivalent to 725 horsepower. As you can see here, 725 horsepower boiler. So we're talking about, some considerable energy here that can be recovered and used. If we look at this from a dollar and cent standpoint, a 725 horsepower boiler, 25,000 pounds per hour, if it operates 24/7, 8,760 hours per year at 55 cents per therm for natural gas, it's going to equal about almost $1.2 million a year in fuel expense. Now, if we take this and look at the average spend in an industrial facility, as far as its operating cost is concerned, a considerable amount of that operating spend is in fuel. And so that's why this is so important that we look at this particular strategy, combined heat and power, not just from the motive standpoint of what it can do, but also look at it from the standpoint of cost reduction and its impact on the environment as well. Because if we take a look from an environmental standpoint, there are 400,000 commercial industrial boilers out there. 60% of those are over 20 years old, and many of these are operating at 75% efficiency or less. We consume 33 quadrillion BTUs per year as a country. It's 25% of the world's energy. 21 million barrels of oil a day. We waste, based on this 75%, we waste about 400 million barrels a year. Now, the Gulf oil spill was 172 million gallons. This is 400 million barrels. And I think when we're talking oil, that's like 52 gallons per barrel. So, in other words, if we burn less because we're recouping all this energy, we pollute less. So conservation is key. So I think in this whole discussion today, it's not just about dollars and cents. It's not just about creating another motive force. It's about conserving energy because it's a finite resource that we're burning oil and gas. And then the pollution, the pollution or the effluent coming out of that stack. So with this as a little bit of background, let's now just spend the rest of our time today looking at some of the heat recovery equipment employed to recover the energy from a couple of sources, beginning with a 5 megawatt gas turbine. Now, what I'd like to do for this is create a scenario here. We've got a specification that's been developed. Now, we've got a facility engineer, we've got an environmental engineer, we've got an energy engineer in a company. They've aligned themselves with a mechanical engineer that's good with combined heat and power. They've decided they want to generate their own electricity. It's going to be a 5 megawatt generator. And they know that that's going to produce 25,000 pounds of steam an hour. Our specification is calling for high and low pressure steam because we've got, in this particular plant, we have some condensate that's being trapped a long, long way away from the powerhouse. And the best way to get it back to the powerhouse itself, to the deaerator or feed tank or whatever, is through a steam motive pump. So let's say we've specified Armstrong International steam motive pumps. We also have compressors out there. That needs some motive force. And we've got a hot water need. So we can generate hot water for CIP or domestic use, whatever it might be. So we're going to take that steam, low pressure, high pressure, whatever it is, go through a PRV, and generate hot water through a shell and tube heat exchanger. Now, the other thing with this particular plant, though, is it's got a very, very small space requirement. Okay, it's an existing plant, and I've got to get this boiler in here. And so I need a very small footprint if I'm going to go with with an HRSG, combined heat and power. I also want to have optimum efficiency. You know, I just spoke about environmental impact, finite resources, and the cost of the cost spend for operations. We want to reduce that cost as much as we can. So I want efficiency here. And I also want to have something that's easy to maintain. That's another requirement because I've got a limited staff. I've got staff, boiler operators, and facility people who are not that familiar with HRSGs. So I want to make sure that when we teach them and train them about how to maintain and how to operate, they understand how to be able to inspect and clean this unit and do it fairly easily. So that's my specification. What we've done here is the engineer has now looked at it. They've selected a partner, and a design engineer selects a slant water tube boiler for their heat recovery needs, the HRSG. Why? Because, well, as you can see here, it has an offset upper drum from the lower drum, diagonal, right? We've got isolated downcomers here, both in the front and in the rear. Now, it also has a high thermal efficiency, and that's one of the reasons why the engineer has selected this. The reason it has a high thermal efficiency is because of the rate of circulation in this particular design. It's got these isolated downcomers, so I've got an excellent pressure density differential between my upper drum and my lower drum. It's almost like the old coffee pots, the old percolators that were sized so that once that water was heated, it being less dense, it finds the riser tubes and begins to explode up here in the upper drum and release its energy, latent energy, if you will, forming steam, right, at the upper drum. This pressure density differential then, with these generous downcomers isolated, allows this boiler to circulate very, very rapidly. When I've got good circulation on the water side of those tubes, it allows me to extract more heat from the effluent, the hot effluent coming in. That will then, increase the overall conduction across the tube and then give me good convective heat transfer within the tube itself. Now, you'll notice here that it says either bare or finned tube heating surfaces. So this unit could be equipped with fin tubes with bare tubes, or a combination. And we'll talk about that a little bit later. But the design engineer knows that we cannot put undue pressure, back pressure, on that turbine, or we're going to start to really cause havoc with the overall combustion. All right? So we've got to be concerned about pressure drop, and we'll talk about that a little bit later. But that's what's been designed. Now, when I talk about being able to transfer the heat, of course, and getting into what we call heat transfer coefficient of the surface. And what heat transfer coefficient refers to is the value of the heat flow across an area as it proportions to the delta T. So what I want to make sure I'm doing is that when this gas comes in, that I'm absorbing as much as I possibly can with every inch of tube, so I can transfer those BTUs to the water and generate steam, which also then enhances. It's like a catch-22. As I enhance the thermal efficiency within the unit itself, I change the density, and my pressure density differential, of course, maintains itself, and I get rapid circulation. So that's what we're looking at here. This is a cross-flow design, so you can see that my gas is coming in from the turbine here and exiting just on the other side. So it's a one-pass design. Now, what I could have done, if headroom was not a problem, one of the things I might have looked at was a drum-over-drum heat recovery HRSG unit. Now, it could either be cross-flow, as you see here, so I've got one pass coming in on the left side, exiting on the right side. It's a small footprint. It would allow me, because of the larger drums, to give me better separation of steam if that was an issue. In other words, I might have drier steam coming out of this initially, even before a superheater. The other thing that I can do with a unit such as this is I can membrane construct it. On this unit that you see here, I should say well, you can see right here, with this cross-flow unit, the insulation around the convective area of my boiler is high-temperature castable or refractory. Now, that could be stainless steel lined as well, depending upon the application. With this boiler, I can also membrane it. So I get away from the castable. I get away from this inner casing, if you will. Another maintenance headache. So this could all be membraned. And I would just then have to insulate and lag it on the outside with my casing, and that would be it. And I'll show you that in a little bit. Now, the other thing that I can do with a design like this is I can go straight through. So rather than going cross-drum, as I do here with a cross-flow unit, I could go from front to back. In other words, this is my target end of my boiler. This is my entry point right here, as you see with the arrow. I come straight through here. With this design, I could also include a furnace, or this could be completely tubed. I've got nothing but convection surface here, or I could have radiant and convection surface with this type of design. Gives me more flexibility there. So that would have been something I would have looked at very seriously, but because of the headroom problem, I didn't go with that. Now, looking at one of these cross-flow drum-over-drum designs, you can see that my hot effluent coming from an oxidizer, it could be coming from a gas turbine, it could be coming from a reciprocal engine, coming in on the side of the unit, going right through, up and out the stack. This is a cross-flow design. Now, when I put all the pieces together for this particular job, you can see that I'm coming in here with my gas turbine, hot gases, so many pounds per hour, depending upon, this is 5 megawatts, so we're talking maybe 150,000 pounds of gas per hour at 900 degrees. Well, in this particular case, I need more mass, and I need more mass flow, and I need more temperature. So I've introduced a duct burner here as well. Now, if this turbine is down for whatever reason, I still have my process needs, I still have my facility needs, so this duct burner will then provide all the energy, thermal energy I need to be able to operate this boiler as though it was being, was actually utilizing the gas turbine effluent coming out of it. So when that gas turbine goes down, I've got my duct burner. Well, it needs air because the turbine is providing me oxygen. The effluent coming out of that gas turbine has got quite a bit of excess air. So I can use that for combustion in my duct burner. But if the turbine is down, I need a source of fresh air for combustion. That's what this is for, a fresh air fan. I come through the transition, come into my HRSG, coming out of the top. Now remember, with this particular design, we said we wanted to optimize the overall efficiency. To do that, what I've added now is an economizer. Now, I've got natural gas being burned in my turbine. I don't really have any constituents within that gas that would be harmful to my economizer. Because it's natural gas, I'm not too concerned about the dew point. That's about 130 degrees. I'm operating well above that. And then my exhaust stack. So this is the system that we've now put together as a result of that particular specification. Now, one other thing that the spec called for was ease of maintenance. Remember I mentioned that thing about our staff, our boiler operators and facility people. They needed some help here. So we want to make sure that some of the critical components can be inspected and cleaned where need be. So you've got generous manways in both your upper drum and your lower drum to be able to inspect and or repair. You also have access ways that will then expose, you can see one right here where I've got this little red dot. That's an inspection and manway there to get us into the convection zone to be able to inspect and clean these tubes. So maintenance was therefore handled in that particular way. Now, this customer in this particular case was also saying, you know, our business is expanding. And what we've designed so far is fine for the immediate needs. But later on, we might be requiring some additional capacity. Well, we started off with this cross-flow diagonal boiler. Later on, we could easily handle additional capacity by putting in a drum-over-drum boiler alongside of it, cross-connecting our downcomers and our steam outlets. So everything is now coming out of this main evaporator, if you will, this drum-over-drum boiler. I also have my duct burner, which is now increased in size because I've got more capacity now. And because of that, I need some post-combustion cleanup as far as emissions are concerned. So I've included a selective catalytic reduction, we'll talk about this a little bit later, unit right here to be able to take out the nitrogen oxides, the NO and NO2, from the combustion gas. And of course I've got my economizer here, as we had before. This now would probably have to increase in size again because I've got a larger load now, so I'm going to have more condensate, more feed water that's going to have to be mass flowing through that economizer, so it's going to have to be a bit bigger. But all I'm trying to show you here, though, is that all of these jobs, when you get into combined heat and power, are highly engineered. We've got to look forward. We've got to try to anticipate what the needs might be, not only for today, but for tomorrow as well. And that's what these partners I talk about, that's what they can do. That they can work with the consulting engineer. They can work with the facility people, the energy people within the confines of the facility itself, and come up with the best solution. Highly engineered. It's not an off-the-shelf item. Now, the next scenario I'd like to discuss today would be a thermal oxidizer. Now, in this particular case, we've got a thermal oxidizer that's generating about 300,000 pounds per hour of gas coming off this oxidizer at about 1,500 degrees. It would be, that's equivalent now to about 50,000 pounds of steam per hour. We're driving a 10 megawatt generator now, not a 5, but a 10 megawatt. So 50,000 pounds of steam per hour could be generated at 200 pounds with that mass flow of 300,000 pounds per hour and 1,500 degrees. That's what we could generate. Now, in this case, they want some superheat. And normally with a thermal oxidizer, superheat could be a problem, okay? I shouldn't say superheat. They wanted supplemental firing, okay? And the supplemental firing normally is not required with a thermal oxidizer because of the amount of gas coming off of it and the temperature. But in this particular case, they were concerned about the fact that the thermal oxidizer is not going to be operating all the time. They've got certain processes that are not operating all the time, so they don't have that. They don't have to incinerate those fumes. But they've got process and facility needs where they want to be able to generate the steam to satisfy those needs. So they needed a duct burner then, supplemental firing, to be able to accommodate those situations. They also wanted an economizer. And when it was looked at, the effluent coming off of the thermal oxidizer did not have constituents that would, like high sulfur, if you will, that would cause cold end corrosion on that economizer. So in this particular case, it was elected that the economizer could be installed. Many times economizers are not used with thermal oxidizers because of the constituents within the gas itself that could be corrosive. So, the engineer for this particular job then selected a drum-over-drum O-type heat recovery steam generator. It has membrane walls. It also has a furnace. Now, why is that important? We come in here with our hot gas at 1500 degrees. Now notice here we have a bypass assembly. Now if for some reason this boiler is down for inspection, maybe it's got we have to replace a tube, whatever it might be, we want to be able to still drive that generator, okay, the 10 megawatt generator, but then the effluent coming off of that thermal oxidizer has got to go up the stack rather than being recovered. So that's why this diverter is here. We've got the inline duct burner right here, but notice where it's mounted. We don't have any transition piece here, which would actually act as a furnace if we didn't have one. We've got a furnace right here in the boiler. So that duct burner is now taking that radiant energy and it's going into the furnace, and we're generating steam through radiant energy or radiant conduction convection, if you will. It's a water tube boiler. It's membraned. It's got the economizer, as you can see here. And it also has a condensate heater to absorb additional BTUs that would normally go out the stack. So that condensate heater, of course, we've got condensate coming back at a relatively cold temperature, relatively cold to the steam temperature. It's probably laden in oxygen because it's seen atmosphere. So it's got to be heated before it goes into the deaerator, but recovering that thermal energy. We also had a superheater. So I'm taking steam off the top of my boiler, bringing it into the superheater section. This would be a radiant superheater now, coming out and then going to possibly a steam turbine to generate more electrical energy, which would then be a combined cycle operation. And here you see the gas manifold here on my duct burner, the effluent, of course, from the oxidizer coming in here. A little closer look at what one of these drum-over-drum O-type boilers would look like. You can see this membrane construction, very rugged. Our isolated downcomers, as I spoke of before. The upper drum, large, for good steam disengaging and accumulation. My mud drum down here, downcomer here. And of course, in this particular case, it's got a top outlet. With these boilers, I could also, with that roof penetration problem, I could have a side outlet on either side to be able to overcome that particular hurdle. As far as the membrane construction is concerned, right here is the outer wall. Of course, inside here is my furnace or the convection bank. I just have a layer of insulation and then my outer casing. So I'm getting away from all that castable refractory problem. So this, again, was a maintenance headache, something that can be alleviated by going to membrane wall construction. I mentioned the fin tubes before. The main reason for fin tubes, an engineer is going to be taking a look at this. Possibly it's a cost reduction method, okay? Because the more effective my convective and my radiant and convective heating surfaces are, the less tubing I have to put in that boiler. So I might want, if it's possible, I might want to go to a fin tube. Either the entire convection section could be finned, or it could be a combination of fin and plain tubes, because I can reduce the pressure drop going through the unit that would be imposing back pressure on my turbine. But the whole idea is to arrive at not only a high heat transfer coefficient, but a high Reynolds number. So what's the Reynolds number? Well, as you see here, it's the ratio between the viscous and inertial forces. The more inertial I can be, where I'm not laminar flow going across that tube, if I can break up that lamination of hot gas as it comes in contact with the tube surface itself, I can raise my Reynolds number. I can raise the heat transfer coefficient. That's what I'm looking for. And that's what these engineers look for. Because they're concerned about cost. They're concerned about space. They're concerned about efficiency. What can I do to maximize the overall opportunity for my customer? Now, as far as the duct burner is concerned, let's just spend a little bit of time on that. Here you see the duct burner, which in some cases we need more mass flow, we need more temperature. I'm only coming out of my gas turbine, for instance, at 900 degrees. Well, I might want to elevate that temperature to more like 1400 degrees so I can maximize the overall efficiency of this unit. Give me the pounds of steam per hour that I need at the pressure that I need. That's what the duct burner will do for me. Now, these duct burners come as a package. They mate up either they're firing into a duct, as I showed you before, or mated directly to the burner itself or the boiler itself, if in fact it has a furnace. Now, they've got to be designed in such a way so as not to create, when the duct burner is not operating, I'm coming out of the gas turbine, I don't need any more than 900 degrees for this particular process, whatever it might be at that point. I can't have a large pressure drop across this duct burner that would impose a back pressure on my turbine. So they've got to have a lot of open area. But they also have to be designed in such a way to give me, when that duct burner is firing, that I get good mixing, I get good contact, so I can limit the amount of nitrogen oxides coming off of it, lower NOx, also get complete combustion without creating carbon monoxide or CO. So if you take a look closely at these duct burners, you have what they call stabilizer cooling. Okay, these stabilizers are like a diffuser on a burner. So as that gas is coming in, it comes across these openings and it turbulates. As it turbulates, it picks up the gas coming out of these nozzles and gives us good mixing for complete combustion and no CO, or very, very low CO. And also we've got this excess air coming in, whether it be delivered by the fan or whether it be delivered by the gas turbine itself. We have this relatively cool gas coming in and air coming in, which is cooling these stabilizers as well. So it's doing two functions. It's helping us oxidize the fuel, and it's also cooling the main components of my duct burner, and also providing some cooling to the flame without quenching it to lower the NOx. That's how these are designed. So far we've been talking about, capacities, HRSGs in the 5 to 15 megawatt range. Let's now spend a little time looking at the bigger ones. In this particular case, I've got 120,000 pounds of steam per hour that I'm generating in this particular unit. This is a modular unit called modular HRSG, as you can see. 120,000 pounds per hour at 800 degrees and 700 pounds. That's what I'm generating here. This is my high pressure generator. I also have a low pressure requirement, 20,000 pounds at 80 pounds. What we call that is optimizing the overall cycle efficiency, because I'm combining both my high pressure and low pressure into one complete package. It also has an integral DA, deaerator, and a stainless steel condensate heater that you can't see here, but that's also included in the overall system. Now, if I take another look at this, here's another example, 190,000 pounds per hour at 750 degrees and 760 psig operating. So these are quite massive. You can see just the relevance here with the guy standing, these two fellows standing here, relative to the overall size. This has got an elevated drum to give us additional capacity and steam disengaging area for our process. Again, highly engineered. All these components are. Note the excess ways here as well to allow the operators to get in and inspect the ducting and get into the boiler itself from here. Looking at some of these schematics now, let's start here from left to right. I'm coming into the first evaporator is really what we call a screen tube section. So I'm taking this hot gas coming in either from my oxidizer or from my turbine. I'm reducing the temperature to a certain extent because I'm absorbing some of the heat before I go into my superheater. I then pass through the superheater into my main evaporator, which also has the elevated drum. So it's one single pass coming through here. I then come into my economizer section, and then, not shown here, I would be exiting out the stack. So that's a very simple once-through arrangement. Now, all of these components are shop assembled, and then they arrive at the job site as these pre-assembled packages then to be bolted together and then piped together and so on. Now, here's another example. In this particular one, if we're looking from left to right now, it's 250 pounds saturated with 525 degrees temperature, 124 degrees of superheat. I'm coming into, as I come in from my turbine, I come into the superheater section first. I then pass in through a screen tube section. Now, the reason I'm doing that is because as I get here, you can see what I'm calling the AIG, which is the ammonia injection unit. This is all working in conjunction with my selective catalytic reduction system. So in order for that to operate properly, I've got to be in the 500 to 750 degree area for this catalyst to work properly. So that's why I'm taking the temperature reductions in this particular area. I then come through here, I come into my main evaporator, which, as you can see, I'm taking steam off the top going into my superheater, which was my first point of entry. And then coming through a combination economizer and condensate heater before I exit up and out the stack. Now notice right here, this particular system, again, highly engineered, has its own little lift crane for taking out the selective catalytic reduction modules, the catalysts, for either cleaning or replacement. Now, speaking of selective catalytic reduction, what that is, it's taking the effluent and treating it through or passing it through a catalyst. In this particular case, what I'm using is anhydrous ammonia, in other words, straight ammonia, which is being ejected into the catalyst along with the effluent of flue gas, reducing the nitrogen oxides of NO and NO2. I also have a dilution skid, and all this is bringing in some ambient air to mix with the mass flow of the gas to increase that mass flow and give me better contact with the SCR. Now our final schematic here, we've got a 300,000 pound per hour system with a duct burner. We're talking supplementary firing, 234 degrees of superheat in this particular one. selective catalytic reduction, and an economizer. So starting here from left to right, what you see right here is this combustion air fan or fan burner assembly right here that I spoke of earlier. I then come into the combination superheater and main evaporator section right here. Superheater and main evaporator section. I then pass through the AIG and selective catalytic reduction portion, then into the second evaporator right here, then into the economizer, and then out the stack. So again, what I'm trying to show here is that all of these designs are unique and vary based on the job requirements and the heat source conditions. So how does one design such a system like this? Obviously, you can't build a beta unit and then test it in the field, right, empirically. So what the answer is, it's availing ourselves with the latest in fluid and thermodynamic tools. We have to simulate and demonstrate the result through advanced computer simulations, and then proving that outcome with mathematical formulas which reduce the complex partial differential equations to smaller linear equations, and then solving those with the use of standard matrix algebra. And what I'm talking about is computational fluid dynamics, as you see here. And also then proven through finite element analysis. So what I've got here is I'm coming in from the turbine exhaust and flowing through the transition ducting to the duct burner. That's what I'm simulating with this computational fluid dynamics. So the mass flow and the temperatures entering this section will ultimately result in the proper duct burner design and the sizing to handle the required load. Now, this information will also be critical in the sizing of the selective catalytic reduction system, including the catalyst and the ammonia injection system. So that's what we're formulating here. Now, here's an example of the furnace modeling when the design calls for radiant surface absorption, where I've got that duct burner connected directly to my boiler, firing into that furnace. So what I'm concerned about here is I want to make sure I've got proper flame shape, I've got proper temperature, because I'm concerned about lowering the NOx as much as I possibly can before I go into the selective catalytic reduction unit to minimize the size of the SCR and limit the amount of cost associated with it. So the flame pattern, the temperatures, the amount of radiant heat transfer in that furnace become all important, and I can simulate that very accurately with computational fluid dynamics. So after looking at the heat exchange, the last component we want to address today is how do we control all of this? Well, if we look at a typical combined cycle application for, let's say, a 30 megawatt generator with supplementary firing, this is the control system that we would probably recommend if we were doing it. First of all, you have to have a burner management system, which essentially is controlling the duct burner, just like it would in a standard fuel-fired boiler. We also have to have a combustion control system that's not only going to be involved in combustion control elements, but also monitoring. So in this particular case, for this job, we've got 3-element feed water control, which is level, steam flow, and feed water flow. We've got variable frequency drives on the feed water pumps because in this particular application, there are times where it's the duct burner that's furnishing all of the energy for my HRSG. And therefore, the evaporation rate in that steam drum is going to be varying. And I've got to, therefore, vary the amount of effluent coming from my feed water pumps to match the evaporation rate. I also have a stack damper position. I got to know if that stack damper is open or closed. I'm trying to mitigate parasitic losses when the unit is not firing. I also have a diverter operation. This is all part of my combustion control. Is that diverter open or closed? In other words, is the boiler down and I'm going to divert that energy? Or is it open and I will allow that energy then to go into my HRSG? I'm going to be monitoring superheat. I'm going to be also monitoring my selective catalytic reduction system, my economizer, my condensate heater, the pressure and temperatures, all of these things. The NOx and the CO readings can all be monitored. As far as the overall control, then I've got these combustion control system and my burner management system working in lockstep together. The combustion control system is now talking directly to my turbine. The turbine is online. I've got to go through a pre-purge. Combustion control system will monitor that. The gas turbine is then enabled. We fire off. That's my burner. Then I've got my diverter. Is it closed or open? In this particular case, I want it open. That's what my combustion control system will do. All PLC based today. Then my burner management system is going to look at the control and safety limits that tie in now to my duct burner. I want to also make sure that I've got turbine gas flowing. That's the oxygen for my duct burner. I want to make sure that my duct burner is enabled for the second purge. I go through pilot ignition, pilot proven, main gas valves energized, main flame proven, just like a standard fuel-fired boiler. The burner management system is going through that sequence. Then I monitor and manage the operating and safety limits. So these two systems then are integrated and working in conjunction with my gas turbine. As far as monitoring is concerned, of course, I can see what's going on with the combustion control system, with my 3-element feed water, my stack damper, and so on, everything that's in gray on your screen right now, and monitoring all of these points. All these graphics are then designed and placed into this programmable logic-based system. Very, very user-friendly, operator-sensitive. I also have a master controller here. So I'm looking at all these points. I'm looking at my boiler, my HRSG, what's going on with all of this. And in addition to that, this master controller can also be integrated with a, let's say, a fuel-fired boiler, where for some reason or another I need some additional steam. So I can bring that boiler online, tie them all together. That, in addition to being able to extract various pieces of information on this system, tabulate this information, trend this information, and then historically file it. So that's the power of the controls that are associated with these combined heat and power systems today. So there you have it, a basic review of the large-scale energy recovery, which when generating your own electrical power through a turbine, exhaust, or having a heat source which produces a lot of recoverable thermal energy to be converted into steam or other uses, installing the right HRSG system can make sound economic sense. Because, you know, when you consider it, many large capacity process industries today, it's not a matter of whether fuel will be purchased or not. It's strictly how much. In other words, there is a certain amount of that energy which you could say is at risk. We can continue to buy and waste part of it, or we can invest capital dollars to save the energy at risk and return the savings to the business as incremental wealth. Now, these large heat recovery projects are not cheap. They can run millions of dollars. But in these businesses, the energy isn't cheap either, as I showed you. And it's an ongoing expense, which, if reduced, can spend considerable cash year after year while returning the company's targeted yield in after-tax dollars. Now, it's all a matter of deciding if the potential is there and then applying the proper financial metrics to justify the financial decision. And there's help out there for that. Going through this analysis of internal rate of return, net asset values, and so on is not easy. Accountants spend a lot of years trying to really understand this and work this out properly. But there's software out there today to help you with this, help you make a good economic decision for your business. So in summary, on-site power generation is more efficient than power from the utility. Over 90% of the thermal energy coming from a heat source is recoverable. Combined heat and power systems are highly engineered to include energy source, heat recovery, ducting, emission control, stack recovery, and controls, all packaged together. Supplemental firing can be over 100%, up to 4 times as a matter of fact. The HRSG design choice and configuration varies by specific application. They're all different. The fuel and emission saving potential is substantial, needs to be justified using sound financial metrics. And then finally, the critical factor is choosing the correct partner to help engineer and provide the system. How about some questions?
Thank you very much, Steve. Appreciate it. We will take questions now. We have an expert panel that is with us, and I'll introduce those in just a moment. If you would you please direct your questions using the question and answer tool on your web